Hello, I'm Shudipto Shekhar Mondol. I am a final year student of Bachelor of Technology in Mechanical Engineering at Heritage Institute of Technology. Today I'll be talking to you about steel making. So, steel is one of the strongest materials on earth. It has changed the course of our history, shaping our civilization and the way we live. But today, scientists are re engineering steel's molecular structure, creating new forms with the potential to build higher, further, and stronger than the world has ever seen. So, steel is basically an alloy of iron and carbon. If the amount of carbon is varied in steel, then it imparts different properties which are used for different purposes. So, yeah, steel is undoubtedly the world's most useful and inexpensive metal. Uh, Steel is yeah, made of crystals, and the dislocations inside the crystals helps the steel to deform. Steel is tough and has high tensile and compressive strength. The dislocations inside the steel crystal is what makes steel so special, because they can move, and when they move they change the shape of the crystal, thus they change the shape of the steel. Thus it also has different applications in the field, applications in construction, automobile, food preservation, aircraft, ships, and utensils. And yeah, and this is basically the last point is basically a quote from a steel worker. So it goes like, steel's design and the use is only limited to the human mind. So the raw materials that are needed to produce steel on a large scale. The first one is iron ore. Iron ore is found near the surface of the earth, and open pit mining methods are used to extract the hematite ore. Giant shovels scoop up huge bites of ore. The trucks are quickly loaded, and the ore is on its way to the steel plant. Underground mining methods have also been known to be used to mine iron ore, that is hematite. Other than this, limestone or calcium carbonate is which which acts as a slag, is also needed for the mass production of steel. Huge rocks are blasted and the stones are transported to the steel industry. I mean, like, limestone are shipped to the steel industry. Other than that, coke, which forms the basic, which forms the main source of carbon, is also needed. Bituminous or soft coal is converted into coke. This takes the place of the charcoal that was previously used as fuel. The coal is first crushed and then heated in ovens until the moisture and the volatile matter has been driven off. After all that, after all the byproducts have been extracted from the non-volatile matter, the gas that is remaining can be used as fuel. After 16 to 24 hours, the red hot coke is pushed out. It usually contains 91 to 92% of carbon. So, see, the all this charge, that is the hematite ore, the limestone, and the coke, are collectively called the charge. This charge is fed into the blast furnace continuously, uh, and 1 ton of iron requires approximately 2 tons of iron ore, 1 ton of coke, and half a ton of limestone, and 4 tons of air. hot blast, hot blast stoves and powerful blowers, which force huge amounts of preheated air into the furnace. Heating the air increases the production and decreases fuel consumption. In striking contrast to the primitive methods, the modern blast furnaces are controlled scientifically. Up through the mass of coke, iron ore, and limestone is blown at a roaring blast of preheat air. The carbon from the coke reacts with oxygen to form carbon dioxide, and this carbon dioxide in turn reacts with carbon again to form carbon monoxide. This carbon monoxide reduces the iron. This is basically what is happening in the combustion zone. Then comes the slag formation zone, that is the calcium car- carbonate. Calcium carbonate reacts, disintegrates into carbon dioxide, and calcium oxide. Calcium oxide in turn reacts with the silicon oxide present in the furnace into calcium CaSiO3, which is the slag. In the reduction zone, carbon monoxide reacts with ferric ferrous oxide to form iron and carbon dioxide gas. So the slag formed in the slag formation zone is collected from the furnace through a slag hole. Every 4 or 5 hours, the tapping hole is opened and out rushes a glowing stream of molten iron. Actually, in the slag formation zone, the limestone combines with the earthly matter of the ore, forming slag. The iron and the slag formed in the molten globules like the iron and the slag form in molten globules like raindrops, which trickle down through the burning coke. A pool of molten metal is formed at the bottom of the furnace. The Bessemer converter. This was the first process in which steel was produced on a mass scale. It was discovered by the English scientist, I think, Henry Bessemer. This process is not used in the modern industry because a large amounts of heat is wasted and the nitrogen content of the steel is too high and it needs too much maintenance. The open hearth furnace. Hot metals from the blast furnace is tapped into the ladle. Iron must be further refined to become steel. Tailor-made steel can be produced in large quantities using this method. First, the limestone is dumped in the furnace. The limestone removes the impurities from the steel. The furnace is then charged with a predetermined amount of steel scrap. As the scrap is already refined steel, it's a helpful ingredient. Lastly, a huge overhead crane dumps huge ladle of hot metal as it comes from the blast furnace. The usual charge is about half scrap steel and half blast furnace iron. An open hearth furnace consists of what might be considered as an upper stairs and a downstairs. The upstairs is the hearth in which the steel making materials are refined. Downstairs are heating chambers containing fire bricks made in checkerboard pattern. one chamber for heating the chamber, which may be oil or gas, and another chamber for heating the air. The predetermined air and the fuel move upwards and pass into the space above the earth. Combustion instantly takes place. Currents of flaming fuel sweep over the hot metal, creating temperatures above 3000 degrees Fahrenheit. Excess carbon and impurities are burnt out. The silicon reacts with ferrous oxide, iron oxides to form silicon dioxide and iron, and the manganese reacts with iron oxide to form manganese oxide and iron. Oxidation and refining uh, also takes place in this process. The hot exhaust gases pass down to another set of checkered chambers, heating the bricks as they pass between them. Every 15 minutes, the direction of the fuel in there is reversed. In this way, the air and the gas is heated in one set of chambers, while the exhaust gases are heating the others. This mechanism continues for 9 to 12 hours. The molten metal is oxidized and undergoes desulfurization and dephosphorylation. From time to time, samples are taken for laboratory analysis to make sure the steel meets the rigid requirements. Tests are carried out in every step in the production system. A production of steel, the metal is then tapped into ladles. The slag, being lighter, overflows from the ladle. The nitrogen content of the steel is low compared to the Bessemer converter. So this process is widely used in the current industry. Now comes the basic oxygen converter, or BOC. It is the most abundantly used process for procuring steel from pig iron. Basic oxygen converter can produce up to 250 tons of steel in a matter of hours. The iron is first oxidized to iron oxide direction oxygen at the molten metal at by directing oxygen at molten metal at supersonic speeds. The iron oxide then reacts with the impurities in the metal and the slag. The iron oxide rich slag dissolves the lime. The dephosphorization of the metal takes place. Then the basic oxygen converter, or LD converter, is a refined version of the Bessemer converter, where the air has been replaced by oxygen. BOC reduces capital costs of the plant, time of smelting, and increases labor productivity. These are the steps that take place in a basic oxygen converter. First, the scrap is charged into the converter, and then the molten iron is charged because there is a predetermined amount of scrap metal charging and the molten metal from the blast furnace, and then then the impurities are burned by blowing by blowing oxygen and flask addition. Sampling is done from time to time. This I have mentioned this previously. And then after the steel is made, the steel is transported to a place where it is casted, and the scrap is discharged from the converter. Ingot cast. I have to say another thing here, because like after the metal goes before casting, the molten steel undergoes alloying. Uh, the molten metal from the basic oxygen furnace is tapped into the ladle. The steel undergoes alloying in the ladle metallurgical furnace, or LMF. Tungsten added to low carbon steel can withstand cold temperatures and has high resistance to pressure. A little chromium can increase the tarnishing resistance and erosion. Uh, Manganese and vanadium increases the strength and flexibility. Ingot casting. This is a really old method of steel casting, and it is not really used in the modern steel industry. Uh, but I will be still be reviewing this process for the better understanding of steel making. So the molten metal from the basic oxygen furnace, or the open hearth furnace, is tapped into a teeming ladle. Ingot casting process of steel making has greatly been replaced by continuous steel casting process. Only about 5% of the total steel is manufactured using this process. There are two types of steaming practices associated with the ingot casting: bottom pouring and top pouring. This particular picture in this slide shows illustrates the bottom pouring practice of ingot casting. There are three types of ingot produced based on the oxygen content: the killed ingot, semi-killed ingot, and reaming steel ingot. Killed ingots are completely deoxidized ingots. Semi-killed ingots are partially deoxidized ingots. Reaming ingots are ingots with excess oxygen in it. This process has been vastly replaced by continuous steel casting process. So, like I have identified the parts. This is the ladle. This is the stopper. To control the flow of the steel. And this is the turn dish. This is the shroud. This is the mold. This is the roll support. And, these are rollers. They continuously they help to push the steel that is casted forward. Uh, 8 sorry. This is the shroud. This is the path. This is the level, or no, this is the meniscus. This is where the steel is withdrawn. This is the slab. Continuous casting solidifies a major part of the 25 million tons of steel produced every year. In this process, a ladle is positioned on top of the holding bath called the turn dish to ensure continuous metal feed. The metal is transported through another shroud into a copper mold, which is water cooled. This solidifies the metal. It also oscillates vertically to prevent the metal from sticking to the mold walls. For hot rolling, hot rolling may be carried out on the metal coming out of the casting machine. After the metal, this steel is rolled It is first hot rolled, and then maybe if needed it is cold rolled. Then it is galvanized to protect it from corrosion. This is another picture of the same process. The ladles pour hot metal into the turn dish, and then from the turn dish it goes into the mold. Then they are sorry and they are rolled, and sheet metals are produced. Strong, durable, and flexible. Steel's versatility is evident in engineering and in architecture. But this metal has also another quality that makes it even more dispensable and resilient. Steel is the most recycled material on Earth. It has 71% recycled rate, which is approximately 4 times combined amount of both aluminium and plastic. Fire explosion may bend or break the steel, but seemingly nothing can destroy it. Even when the steel lies in ruins, it can be melted and recast, molded from another purpose, remolded for another purpose. Uh, its recyclability has changed the way that steel industry operates. For steel, there is no shelf life, no longer confined to the iron ore. Steel industry now uses cans, rail guards, or even an old dishwash as raw material. In recent years, scrap metal has drastically cut down the cost of production and reducing environmental impact. Further advancements should be made to reduce the energy consumption in the steel plant. Uh, Reduction of waste production by using the waste from one industry as a raw material from another industry. For example, slag from the steel plant can be used in the cement industry as raw material. Increasing the purity of oxygen can also improve productivity. Pulverized coal has become a successful practice as it increases the surface area and burns more efficiently. Scientists have continued to strive for new types of steel, new combinations of elements that will give strength and shape to the 21st century. At University of Virginia, material scientists sorry, material scientists Gary Shiflett and Joseph Poon are developing a new type of steel. It is stronger than anything that has ever came before. Darva glass is made by combining iron and carbon with various elements including molybdenum and boron. Darva glass is something completely unique. It is an amorphous steel. In traditional steel, atoms are packed together like crystal. They have a uniform molecular structure throughout, but in amorphous steel, atoms are packed randomly like glass, meaning each cross section is different from the one before it. This jumbled atomic structure produces a steel that is stronger. Like the invention of stainless steel nearly a century before, Tarva glass is a potential landmark. But Tarva glass has a crucial flaw. It is brittle. Unlike most traditional steel, which has the ability to expand and contract under force, Shiflett and Poon are hard at work to correct this limitation. They can find a solution. If they can find a solution, the potential of the Tarva glass can be limitless. Uh, will this new material revolutionize the world? Some believe it has the potential. Even now, with its limited capacity, Tarva glass is already searching for applications. It is currently being tested at the Yucca Mountains repository as a possible ceiling of nuclear waste containment. It has only been 150 years since Henry Bessemer made the mass production of steel possible. In that short time, steel has reshaped human civilization. Steel revolution has stretched the possibilities of human imaginations and redefined our lives. Today, at the dawn of the new century, steel industry is responding to the demands of the future. The one constant about steel is that man drives steel to continuously evolve. And if we learned anything, it's that the story of steel is far from over. I would like to thank the following people who constantly helped me to write the write the research paper and this presentation. These are the references that I used to make the presentation, as well as the research, I mean the review paper that I published. So I would like to thank all of you for bearing with me. If you have any questions regarding my presentation, you can comment, you can ask me in the comment section. I will also include the review paper that I published in a international journal. So thank you.